Can you give us an example for a normal space, for example? Normal space. What's normal space? Because, you know, okay, it has a norm. What do you mean? Normal space. Normal. Okay. Space of continuous functions. What is the purpose of all of that? What's the purpose? The purpose is to generalize the notion of vectors. Okay, we have vectors and we add these special features in the sense, okay, we know how to treat vectors. But if we have other objects that possess the same features, the same essential features like vectors, we should treat them the same way. Okay? So we make these precise definitions so that if any other object satisfies these definitions, then we will find to treat it as we treat vectors. So continuous functions, which we will give the name C0, defined on the interval 0, 1, with the norm. Here is the norm. I can give you the length of f. F is a function. I can define it as integral from 0 to 1 absolute value of f of x dx. This is a norm. This is a normal space. So please treat these continuous functions as if you treat vectors. But why do we ever need this kind of thing? Because sometimes you're doing, say, a control on a rod. You have a rod. Have a rod here, and you're giving some heat here. So you're trying to control the temperature of the rod. T as a function of x, right? You have a desired temperature profile. And you want to measure the error. You want to give a notion of the error. You got some temperature profile, T of x, it's a function. And you have another function that you hope for. And you want to tell how far they are. So are you talking about distances? Yes, I'm talking about distances. How far they are? Well, I can define it because norm gives you a distance. I can define the distance between T1 and T2 of x as the norm of, this is the norm of x, right? The norm of T1 minus T2, as we said, which is, according to this definition, it's T1 of x minus T2 of x, which is the obvious thing to do, but we're making it formal, right? So, what about, so this is normal space, inner product space. Again, I'll give you C0, 0 to 1, with the following inner product. Inner product between 2f and g is the integral of 0 to 1, f of x, g of x, dx. This is an inner product. So if you want to tell me if two functions, if you want to check if two functions are orthogonal or not, right? Well, I complete the dot product and I see if it's close to 0 or not. This gives you the angle between them, right? So I will now introduce a concept for these guys because I'll ask you the question. We learned that Z was not complete, right? We add some numbers, we got Q. Q was not complete, we added some numbers to get R. These are spaces, and here we're introducing larger and larger spaces. So I'm asking you, is C0 complete? Does it have all the functions? Is it, if you have a sequence of functions, if they converge, will they converge to a continuous function or not? Well, the answer is no. Why? Because I'll give you an example here. Look at this. F n of x, this is a sequence of functions. It's x to the power n. It's you know, the simplest thing ever. So this is 0, this is 1. X to the n. It's, you know, everybody's familiar with it. So like x to the 1, this is the first one, first function. X squared, the second function. X cubed, the third function. X 4, 5, and so on. So you can now guess if these guys converge, they converge to what, right? So let's write this by black. So if these guys converge to something, they converge to what? Let's see. So all of them, they are 1 at 1, so obviously the function will be 1 at 1. And you can see as you go higher and higher, all of them, they have the flat thing. So it will be 0 all the way open here, right? And it's 1 at 1. So this is really the limit. It's 1, x equal 1, and 0 if x between 0 and 1 open. This is the limit. The red one obviously is not continuous, right? So a sequence of continuous functions, they converge, but they converge to a function that is not continuous. So it's not complete. We should add these limits. We should add this function to the continuous functions and all the other limits to make them complete. And when you complete it, so now here is the thing, because if you ever hear these words, I want you to be aware of them. So normed space, if you have a norm, plus completion, we get something called Banach space. If you add the dot product, the inner product, which is the best thing to have, the inner product, right, plus completion, you get Hilbert space. So what's Hilbert space? Is nothing but a place that you can do inner product, right? It's like vectors. I can define orthogonality. It's the best thing, the best feature to have, because if I can define angles, I can define length of curves, I can define distance between points. It's the best thing, and it's complete. So this is the Hilbert space. So it's a generalization of Euclidean space of our vectors, because our vector is just finite dimensional. If you have x and Rn, it has inner components. This guy may be infinite. We're talking about functions. So actually, here, if we have C0, 0, 1 with the inner product that we said, and it's not complete, if you make it complete, so if you add completion, you get the L2 space. So the L2 space is a Hilbert space. Okay, and what you get? So what do you get out of that? Anyway. Okay. What you get out of that? Why we're making it a big deal? Because again, I want you please to treat anything that satisfies this, that's a Hilbert space, like you're treating vectors. How we treat with vectors? How you, and this is L2 functions, for example. It's functions. So it's much larger. How you treat vectors? Well, we can define what is x perpendicular to y, right? It means that the dot product of x and y is 0. That's the same thing here. F perpendicular to g is equivalent to the dot product of f and g is 0. Actually, I can have a basis in the sense I can have a basis. What do you mean by basis? Like basis in Rn is what? Is 1, 0, 0, 0, right? 0, 1, 0, 0, 0, and so on. So here we have a basis for L2. What are these bases? Sines and cosines. So e to the I n x phi n is, this is E1, E2, and E. For Rn is just up to En, right? Here we have infinite. So this is e to the I n x, and sometimes we normalize by square root 2 pi. So it's cosine nx plus sine nx, right? So cosine and sines are really the basis. And whenever you have a basis, you have what? I can expand any vector in Rn. I can expand it as coefficients in terms of these bases, a1, e1 plus a2, e2, and so, right? The exact same thing here. You have a function in L2. You can expand it as a1, sorry, this should be 1, plus a2, phi 2 of x, plus yada yada, right? How do you get these coefficients? Here, how do you get the coefficients? Anybody remembers? AI is what? Simply the dot product of v and ei, right? It's the exact same thing. Now to get the coefficients here, it's the dot product of your f and the phi I is the exact same thing. But the dot product here, we know how to do it, and now we know how to do a dot product in this infinite dimensional space. We just do the integral, right? So it's the exact same thing, the exact same analogy. Please deal with the two functions as vectors. They are indeed vectors, nothing more, right? Yeah, that's good. We have like 7 minutes. I finished most of what I wanted to do. Do you have questions? Yes?
Yeah, so we do have several bases for Rn, for example, and by analogy, we should have several bases for the...
You can, yeah. Sure.
So there is can we establish a bijection between those?
Sure.
There is a bijection.
Yeah. So, anybody remembers what's the name of this guy? This guy?
Fourier.
It's Fourier expansion, right? Fourier series. Right? Yes. The expansion of this, it's nothing but actually a representation in the basis. When you see it this way, it's very natural. I mean, you don't need to give it a name. So, so this is all what you get from abstraction, right? This is why abstraction is useful. But actually, since we have 5 minutes more, I will give you more examples. I'll give you one more reason why we may need abstraction. Because to avoid subtleties. Maybe I don't know if it's right or wrong. To avoid subtleties and weird examples. What do you mean by weird examples? Well, mathematicians are super good at coming up with weird examples. Can you give me a function that is nowhere continuous? I mean, we tend to think about functions as something like that, right? How are you gonna plot it without being continuous, even at a single point?
Just dots.
Exactly, dots, right? It has to be very weird function. This is the function that's nowhere continuous, like f of x is 1 if x is in Q, and 0 if x is irrational. Right? So it's like this is 1, then 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. So, so how to make it continuous on all irrationals but not? So I'll keep it not continuous on rationals, but I want to make it continuous here. How can I do that? That's very hard. Well, there is an example. Okay. So, but I'll give other examples that might be more interesting. A function that is continuous at only one point. How we draw the function such that it becomes continuous at just one point and then drops all of a sudden. This is very hard because, you know, as we know, if you just, by drawing, if you just make it continuous, just any line means that infinite number of points. Right? Any line, no matter how small it is. Well, we can come up with a definition, that's fine. F of x is actually x and negative x. The same thing here, x is in Q, x is in R minus Q, so this looks like the following. So if x is in Q, it goes like x. But between them, it goes like negative x, right? This is here, 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 here. Between these guys. So this is here, and so on and so on. Okay? But you can see, what do you mean by continuity? Then now it invokes a more rigorous definition of continuity. And you come and say, okay, continuity means if I didn't change much, the function shouldn't change much. And you find that, yes, here no matter how small you change, you'll drop immediately down and up, down, up. So with all these points, it's really not continuous. But here, if you didn't change much, it will not change much because it's all around here, right? So differentiability is even harder. Why? Because actually one of the things out of Darboux theorem is that you can't have jump discontinuities in derivatives. Derivatives. What do you mean? So a derivative of a function can't be. So if you're telling me that this is f prime, right, of a function, I'm plotting the f prime, and you're saying f prime is like this and that. No, this is wrong. This can't be an f prime. What do you mean? Yeah, it can't be an f prime. So f prime of function can't have jump discontinuities. So I'll give you a counter example. Whereas here it is. It has a slope that is -1 and 1. That's right, but it's not actually differentiable. So this is not a differentiable function. Okay? It doesn't have a derivative. If you have a derivative, then it can't have jump discontinuities. Okay, very good. But after knowing that, can you come up with a function that is differentiable at only one point? Differentiable at one point. So after knowing this fact, it's very hard to think about it because you just said that we cannot, we cannot play much with derivatives. We cannot have jump discontinuities. Now you're asking me to have a function that is differentiable at one point. And not only that, and nowhere continuous. It's not like it failed nowhere continuously. Well, yeah, actually, if we integrate this guy, we'll have the same thing. So f of x is x squared, negative x squared, x in q, x is out of q. You can keep constructing. I will not hold you here for. But there are many examples. I'm just citing some examples from analysis. You can cite similar examples from any other branch in math. So the fact that we rely solely on our intuition, like we engineers will have to do that, that's really good. But it shouldn't be solely. Rely on your intuition, but not only on our intuition. Whenever you have an intuition, a conjecture, we should have a mathematical justification for it. It's like, you know how if you took 275, I don't know if they do it here or not, but in 275 nonlinear systems, we call Lyapunov things certificates. Because it comes with a certificate. Whenever you have a mathematical proof, it's a certificate. It's not debatable at all. So this is why, abstraction is useful, because you can always find very weird examples that you will never expect. And if you rely solely on your intuition, you will fail. Your theory will fail. Okay? And this is the difference between a theory and a theorem. Theory is maybe based on intuition and observations and physical observations, but a theorem is not debatable. It's just a mathematical certificate. Okay? We're done. Any questions? This will not be in the course, but this is the language we're